A differential equation involves an unknown function and some of its derivatives. And unlike most functions you've encountered so far, we're not solving for a value of x. The solution to a differential equation is the unknown function. So it tells us that the derivative of some unknown function y is equal to ky. And so we want to find the unknown function y. And since the addition of a constant to a function has no effect on the derivative, for example, 2x plus 3 and 2x plus 4 have the same derivative, that means there are actually infinitely many solutions to a single differential equation. Here you can see a graph of all of the possible solutions to some differential equation. They're all the same function, but they differ by adding some constant. So they all have the same derivative, but the graphs are all different. So most of the time when solving differential equations, you'll have what's called an initial value. They might tell you at x equals 0, y is equal to 1. So that way you know that which particular solution you want. So if they give you the initial value 0, 1, then you know that you want the solution curve that passes through this point 0, 1. So we'd want this curve out of the family of solutions. So even if we can't solve a differential equation, we can visualize this set of solution curves by creating what's called a slope field. So because we have the differential equation, we can easily find the derivative of the solution at any point. So we know at each point what the slope of a tangent line to these solution curves will be. So we can sketch these mini line segments according to the slope of the tangent line. So for example, we have the differential equation dy dx equals negative x over y. So we can plug in various points. So at 0, 1, the derivative will be 0. So we go to 0, 1, and then we draw a horizontal line, because if the slope of the tangent line on the solution curve is 0, it must look like this. It must be horizontal at that point. So then we plug in more values. At 1, 1, we have a slope of negative 1. So we draw a downward slanting line segment. And then at 1, 0, we have an undefined slope, because the bottom of the derivative is 0. And so we can guess that this means it will be a vertical line. So if we plug all the other points in, then we'll get something like this. And from the slope field, you can visualize what the solution curves will look like. So we see that the set of solutions are probably a bunch of circles based on the slope field. So let's do one more. We have the equation dy dx equals y times 2 minus y. And this time they give us a initial value at x equals negative 1, y is equal to 1. So again, we plug in different points, and notice here the derivative does not depend on x. So all we have to do is plug in y values, and for all points where the y coordinate is this value, the slope will be the same, because it does not depend on x. So we have two y values where the derivative is 0. So we can infer that we have two asymptotes in a set of solutions. And we want to draw the particular solution that passes through the point negative 1, 1, which is right here. So following the slope field, we can sketch out the graph. If we wanted to draw the solution above this line or below this line, then they might look something like this. And notice how the steepness of each line segment depends on the derivative. For example, at y equals 1, a slope is 1, so we have a normal upward sloping line. And then at y equals 3 and negative 1, the derivative is negative 3. So we want to make the line a little steeper. So if they give us an initial value for a specific solution curve, then we can use a linear approximation to find the value of the solution at any x. And we want to use multiple linear approximations, because if we just do one, it'll be a lot less accurate. So here you can kind of see what we're going to do. If they give us this initial point here, then we know the slope at this point, so we can make a linear approximation and go and approximate the y value at this point. And then at this point, the derivative is different, so we can make a new linear approximation and approximate the y value at this point. And then we can make another linear approximation to get to here. So it's important to note that all we're doing is making a tangent line and using a linear approximation. It's not some new formula that you have to remember. So if we're giving the initial value x1, y1, then we can write the tangent line y minus y1 equals m, which is the slope, and we know the slope because we have the differential equation, which tells us the slope of the tangent line at any point, and times x minus x1. So if we start at the initial value and travel a distance delta x, then we can predict the y value at the new point to be the derivative times the change in x, which is this part, plus the initial y value. And this method to approximate the solution to differential equations using tangent lines is called Euler's method. And so, of course, the smaller step sizes we use, the more accurate the approximation will be. So if we have the equation dy dx equals x plus 2, and the initial value 0, 3, and then we can approximate the y value at x equals 1 using Euler's method with 2 equal steps. So 2 equal steps means we take an interval, we start at x equals 0, and we want to approximate at x equals 1. So if we want 2 equal steps, we'll use a step size of 1/2. So first we'll approximate the y value at x equals 1/2, and then we'll approximate it again at x equals 1. So at an initial point 0, 3, the derivative or slope of the tangent line is 2. So then we write the first tangent line approximation. A new y value at x equals 1/2 will be the slope times the change in x plus the initial y value. So our slope is 2, our change in x is positive 1/2, and our initial y value is 3. So we approximate the y value at x equals 1/2 to be 4. And then now we have to calculate the new slope at this point, 1/2, 4. So the new slope is 5/2. So then we make another tangent line. The y value at x equals 1 will be the slope 5/2 times the change in x, still 1/2, plus the y value at this point, 4. So we get an approximation for the y value at x equals 1 is 21/4. So let's do one more. We have the equation dy dx equals x plus 2y, and the initial value 0, 1. And we want to approximate the y value at x equals negative 0.6, using 2 equal steps again. So going from 0 to negative 0.6, 2 equal steps will be negative 0.3. it's negative since we're going backwards. So the derivative at the initial point is 2. So then we make a tangent line. F at negative 0.3 will be the slope, 2, times the change in x, negative 0.3, plus the initial y value, 1. So we approximate it to be 0.4. And then at this new point, negative 0.3, 0.4, the slope is 0.5. So a final tangent line to approximate f of negative 0.6 is 0.5 times negative 0.3 plus 0.4, and we get 0.25.